Welcome to the Highland Wonders Podcast, where we share stories and knowledge from experts about the charismatic species and diverse ecosystems of the Okanogan Highlands of north central Washington. My name is Jen Weddle, and I am a co-director of Okanogan Highlands Alliance, a nonprofit conservation organization dedicated to protecting the beautiful Okanogan Highlands, the traditional and ancestral lands of the Okanagan First Nations in British Columbia and the Okanagan Lakes and Colville bands, who are now part of the Confederated Tribes of the Colville Reservation. We are super-duper excited to be back with Season 3 of the Highland Wonders Podcast, and we want to welcome you back as well. Thank you for listening. We have an exciting and still evolving lineup of topics and experts this season, but we are kicking it off with a dive into the past. How far into the past? Well, it depends on your perspective. Once upon a time might mean totally different things to different people. So I thought it might be fun to try and think about the geological time scale. That's always a little bit mind-boggling. Let's say that Earth formed at midnight, and right now is the following midnight. So we are putting Earth's 4.6 billion years into a 24-hour timescale. Using this analogy, the first forms of life appeared around 4 a.m., but it wasn't until 8:30 p.m. that the living world really began to diversify. At 10:56 p.m., the dinosaurs appeared. Our species, Homo sapiens, only showed up about 76 seconds ago. That's about 300,000 years. And so the last ice age, which was finishing up about 10 to 25,000 years ago, was seriously barely more than a snap of the fingers into the past. But yet, that last ice age had major impacts on the landscapes of the Okanogan Highlands. And that is what this podcast episode is all about. Karl Lillquist, geography professor at Central Washington University, leads Ice Age field trips all over eastern Washington. And here he examines how the landforms of the Okanogan have been shaped and sculpted by ice as it moved, as it sat still, as it melted and retreated from the Okanogan during and at the end of the last ice age. Dr. Lillquist has been thinking about this stuff for a long, well, not long geologically speaking, but a long time. He grew up in Orville and spends time in the Highlands every year, pondering the origins of some of our most iconic places. It's pretty amazing the ways he has amassed information, sometimes from unexpected places, in his efforts to build the story of how this place came to look the way it does. This episode is distilled from the recording of a recent field trip through the Highlands. And part of the fascination is listening to Dr. Lillquist apply his understanding as he puzzles out the various ways that unique landforms, from large fan deltas to snake-like eskers to stair-stepping terraces, may have come to be. He offers explanations, but, and this is an exciting part, as you listen, it becomes clear that nothing is set in stone. Ha ha ha! There are unanswered questions, exceptions to rules, a lot more to learn about why our landscape looks the way it does. And this podcast is just the tip of the ice sheet. We anticipate that after listening, your curiosity will be piqued and you will want to learn more. Well, we have good news. Dr. Lillquist, in all of his amazingness, also wrote a field guide, which you can find on OHA's website under Education News. So enjoy!
The glaciers sculpted the underlying rock, and what we see up here is the glacial modification of the bedrock and its tectonic heritage, its faulted or jointed heritage. In the Okanogan Highlands, there are all the rock families. There's the igneous rocks that can be volcanic, or they can also have formed beneath the Earth's surface and cooled. The volcanics up here, I think there's basalt and there's andesite. Those cooled at the surface, and there were volcanoes here, and when you get into central BC, there's quite a volcanic field up there. Then there are sedimentary rocks. And I know up the Smilkameen drainage, there's sedimentary rocks there that are where there's fossils. Then there are metamorphic rocks here, like there should be slate and quartzite, stuff like that. So you've got all those three rock families, igneous, sedimentary, and metamorphic here. We're in a great part of the world for diversity in geology. Today we're going to talk about two types of glaciers, ice sheets and cirque glaciers. So an ice sheet is a glacier, but it's unconfined by topography. It's just spreading out over the landscape. And a alpine glacier, of which a cirque glacier is a type, is confined by topography. When you get into alpine glaciers, if we were to go into the Cascades, in the parts of the Cascades that weren't covered by this ice sheet, the terrain is much craggier. It's steep and sharp. And these are the kind of glaciers that are mainly in the Cascades now. You don't find ice sheets in the Cascades now. You find cirque glaciers, and they're going fast. So the Laurentide ice sheet went from really the east coast all the way out into, I think it got all the way into Montana. And then the Cordilleran ice sheet stretched just east of the Rockies into Montana. Those two may or may not have actually merged. And for those who argue that they didn't, the theory has long been there was an ice-free corridor through which early Native Americans passed into the lower part of North America. So the ice sheets dictated people movement here. Another possible pathway is down the coast too, with a lower sea level. The ice sheet we're particularly interested in was the Okanogan lobe of the Cordilleran ice sheet. The Cordilleran ice sheet formed essentially in the coast range of what's now British Columbia, and it expanded out from there. Part of the Cordilleran ice sheet moved south into what is now the Okanogan Valley, and it really helped form the Okanogan Valley, and that was the Okanogan lobe. There were other lobes of the Cordilleran ice sheet. The Puget lobe extended south into the Puget Sound area to around Olympia. East of the Cascades, there was the Okanogan lobe, the Columbia lobe, the Pend d'Oreille lobe that blocked off and created Glacial Lake Missoula further east, but we're focused on the Okanogan lobe. So this extended south down to a little town called Withrow, which is on the Waterville Plateau south of Bridgeport. That glacier extended south almost to US 2, if you're familiar with how US 2 goes from Wenatchee over to Coulee City. And it reached its extent there about 15,000 years ago, ballpark. This was a huge mass of ice, and in the Oroville area, it was thick. It was over 6,000 feet thick, over a mile thick. I don't know what high spot they used to determine that particularly, but we know that Mount Bonaparte is 7,000 feet elevation. Oroville's under 1,000. Bonaparte had ice on the summit, and that may have been in the last glaciation. It may have been an earlier one. We don't know, but just you look for evidence on high spots. When that glacier covered this landscape and then started to melt after 15,000 years ago, what's interesting is it didn't start to melt in the low spots. It started to melt out in the high spots. And so the high spots were exposed sooner than the valley. The ice still occupied the valley, including the Okanogan. That can affect all kinds of things, and one of them is that it can help create glacial lakes. Glaciers are lake creators. They create lakes by gouging the surface, by eroding. They create lakes by leaving deposits behind which water forms. Also, just the ice itself, if you have a mass of ice still out in this valley and you have the uplands that are melting off, you have the ingredients to deliver all that water, and it filled the valley from Oroville at 900 feet, stretched nearly as high as Molson. And Molson's at what, 2,800, something like that. Usually in glacial lake sediments, there's clay, and there's, better yet, there's silt. Clay is the smallest, and it's differentiated from sand by its size. It's super fine. Yeah. Then there's silt, then there's sand, and then above that you get into gravel, cobbles, boulders. In lake sediments, you shouldn't see boulders, cobbles, gravel, unless they floated in icebergs. So there's an exception there. But usually it's fine textured, and usually it's layered, it's bedded. The water that's running in is loaded with sediment. The sediment settles out. It's settling out well below the top of the water. But above the glacial lake is glacial deposit. That's a part that I struggle with. When you have a glacier comes through, it often removes the evidence of what happened in the past. If you've got lake and you've got glacial, what we call glacial till on top, it tells you the lake was first, and afterward came the glacial re-advance over the top of that. The problem is there's no dates. Where you get advances in the knowledge of this kind of stuff, first of all, it's not of great practical interest, right? At first glance, it may become that way if you're thinking about groundwater and stuff like that, but what you need are graduate students, and you need colleges nearby, and Oroville is isolated. Where's the nearest research university that's been working on this kind of stuff over time? It's the UW. Or in Canada, Simon Fraser, something like that. So you need graduate students and faculty interested, and this is just a long ways. And money, that's right.
It's about a 17-mile uphill drive from Oroville to Molson if you take the Chesaw Road to the scenic 9-mile road, which gives you views west over the valley and informational signs provided by the Okanogan Historical Society, as well as a peek into Canada. From 1905 to 1935, a railroad actually made the journey from Oroville to Molson along a winding route in order to make such a climb over so short a distance. But thousands of years earlier, that 17 miles was almost entirely underwater. The top of that ancient lake can be seen about 2 miles from the Chesaw Road on 9-Mile Road, looking west down onto a flat bottom valley, which is where Karl is standing for this next segment.
I am just struck by the route of the railroad that came from Oroville to Molson and then eventually on to Spokane. That was a heck of a railroad grade to climb up out of Oroville. I think it's 2,800 vertical feet. And they had to make it so sinuous. That's the Oroville to Molson, Oroville to Spokane rail line. It was mining, agriculture, and timber, and so getting supplies up here and getting products off the plateau. This rail line went into Canada, went down Baker Creek to the Kettle River, and then back into the U.S. It wasn't a border like today. So our topic to get you folks excited about is kind of use your imagination here. Down in the valley floor, it's pretty level, kind of a triangle, and a long triangle. A Greek delta shape. It's a real steep end. It is what we call a fan delta. And it tells us that the lake was at least that high. The top of the water, where sediment is dumping into the lake from a drainage, and it was the 9-mile drainage. So water was delivered from ice sheet melting, and it essentially flowed to the Tenasket Creek drainage. Initially, it was into a lake, and it would have been a steep drop after the lake was gone for that water to make it down into Tenasket Creek. The previous path of 9 Mile Creek formed this massive fan delta, and I don't know if I've conveyed to you my excitement over this enough. This is awesome. Man, this is a huge feature. It's 3/4 of a mile long. I don't know how else you form this other than into standing water. Yes, so it's got to be standing water, and it's got to be deep. And so if you were below, if you're going, I'm skeptical, he's talking about a lake that's really deep. This is evidence for it. There was water up here, standing water in the Ice Age, and if we went down and dug into this, I'll bet there's sand and rounded gravel and lake sediments intermixed in that. So if I would take the time, or you would take the time to look at wells excavated up here, if there are any wells in this bottom, they should have penetrated that kind of sediment. And so there's going to be gravel deposits up here, absolutely, they could be tied to deltas, they could be tied to just individual deposits. It just wasn't there long enough to leave eroded shorelines. Sometimes what's cool in Nevada and Bolivia, you can see these big spits. You can see barriers. You can see everything you could see on the coast of Washington, but it's just smaller usually. Here, I don't think it was here long enough. Rock may be too hard here too. But it may be a lake that stepped down over time with melting of ice too. I'll take the more liberal view that it is all one lake, but I don't have good evidence for that. I can't tie this one to the stuff below. But absolutely, you can have lakes, and I'm wrestling with this again on the Waterville Plateau. Over time, as the ice mass melts, you should get a stepping down of the evidence down through the drainage. And you should also get streams cutting into the sediment, leaving terraces.
There will be more on terraces in a few minutes, I promise. But now we are teleporting over to Marianne Creek Road, which is a beautiful, hilly, creekside journey through forests and wildflower-strewn meadows between Molson and Chesaw. These ecosystems, in many ways, are where they are thanks to Ice Age processes, which eroded and deposited sediments and carved waterways. Along this road is a section of land managed by the Washington Department of Fish and Wildlife, the Chesaw Wildlife Area. Parking and walking just a short distance uphill, you can enjoy views of the valley, get a close-up view of a diversity of wildflowers and native grasses, and observe unique Ice Age landforms that have withstood the ages. And, as you will soon learn, it's also pretty interesting to look under the surface.
The other thing I want you to keep your eyes open for, and it is phenomenal up here, the Molson Hill and Havillah and Chesaw areas, to me, are really known for dark soils. And especially up high here, these dark, rich-looking soils, and they were built by grasslands. They were glaciated, yeah, absolutely. The landscape is glaciated. Right, the sediments could have been deposited, but then soil formed in that's got all this organic matter in it. And so look for the rich soils. These are wonderful soils. So they're loaded with organics, and you're going to see some just stuff that is just knocks your socks off. They're beautiful soils, but it's cold. And part of the reason they're organic rich is it's cold. You can preserve the organics better. How I can tell it's wonderful soil is I look at the structure of it, and it looks like crumbs, kind of like coarse coffee grounds. And that tells you there's a lot of organics, beside the fact that it's dark as well. But it's organic rich. The one thing I'm not seeing, and it's probably just my sample size, is I would have thought I'd see earthworms in this. And I didn't see any, but I bet they're here. So one thing, and I don't want to dive into this too deep, soils can get confusing in a hurry, but the other part of the story here beside grasses and organics is that volcanic ash helps make good soils. And I'm learning on that. That's something that's kind of new in my education. If you go to the top of the ridge, the soils are going to be shallower, and they're mapped as a grassland soil called a mollisol. Mollisol just means soft, and the organics make it soft. These down here have benefited more from volcanic ash. Maybe the ash ran down the slopes after it was deposited on this landscape. Maybe it was carried down the slopes, it accumulated down here, or maybe there's just more organics because it's wetter down here. But these soils are called andisols. So there's 12 types of soils, and 2 of them are right here. That's crazy. One on the top, one on the bottom. And these andisols are in grasslands, but there's something about the way volcanic ash weathers, and then it attaches to the organics. So that begs the question, where'd the volcanic ash come from? Up here, I still haven't looked at enough of the landscape to see it, but somewhere in road cuts up here, you ought to see layers of ash, or a layer of ash, and it very well could be Mazama, and that was 7,600 years ago that it was deposited. It's that deep, so 3-4 feet. This area got influenced a lot by Glacier Peak. It's a lot closer, and Glacier Peak had some big eruptions too. So there ought to be Mazama, but it's probably thinner layer, and you ought to have more Glacier Peak. Glacier Peak's about 13,000 years ago. And there should be, if you had a wetland up here and you cored it, you ought to find Mount St. Helens ashes too. But white material on this rock, I think, is calcium carbonate. Calcium carbonate is an indicator of dry places. And we figured at Molson about 19 inches of precipitation a year. There's not enough precipitation here to leach out the carbonate. And that's why you get your hard pan. So these soils should be basic. They shouldn't, in other words, they should be neutral to slightly alkaline if we did a pH test up here. If you got little cheap test kits or just test strips, pH test strips, and if you did the soils here versus down below, these should be more alkaline up here. And they should have less organic matter, which is a harder test up here than down there, but you can at least see it. And it's a function of topography and the vegetation and the fact that you've got fine sediments being transported out of here. One thing I didn't emphasize enough down below is wind is also carrying in the fines down there, and it's blowing it off up here. So good stuff.
The Chesaw Wildlife Area and Marianne Creek Road is not only a good place to observe the soils, it also has some really magnificent, subtle, but magnificent examples of ice-sculpted landforms. Some of these landforms are familiar and recognizable, whether or not you have a name for them. Terraces, those flat benches above the valley floor that look like they may have been the valley floor in the past are a good example. Other landforms are harder for the untrained eye to pick out. Kames and eskers, for example. However, if you know what to look for as you travel through the highlands, you will start to see more and more patterns in the land, the remnants of ancient ice, water, sediment, and bedrock.
Stagnant ice terrain is hummocky, and we're in the midst of hummocky terrain. We're in an area of eskers and kames, K-A-M-E. To get this, the ice had to sit. Eskers and kames form in depressions in the ice sheet where water and sediment go down into those depressions. And in the case of an esker, it was a stream. They take on a sinuous form like a meandering stream. Then when the ice melts, what was once a depression is now a ridge. So the topography has inverted. That's mind-boggling, right? And you can have eskers draped over eskers. It can just be bizarre. Partly because you don't know what the topography of the ice was inside where that stream was. So you can have eskers running uphill apparently because of that. So they formed in a void in the ice. And there may have just been a single hole called a moulin, M-O-U-L-I-N, where the water and the sediment went down into, but then they got down at the base or near the base of the ice. And I've been in ice caves before in Alaska where they are indeed sinuous. So that depression filled up with sediment, the ice melts away. A kame, K-A-M-E, is just a depression. It'd be that depression in the ice that's just that. The important thing is these are made out of washed sand and gravel. And an indicator of them being around is humans stick gravel pits in them. But here, thank God, they haven't been mined away. I mean, this is impressive. So this is stagnant ice terrain. And man, oh man, are they something else. And they're right here in the highlands. And what's even more beautiful, you guys, they're on public land. Terraces could come from a couple different possibilities. One, if you have ice sitting in a valley, imagine this, you have ice sitting in a valley and you have sediment and water being washed down next to the ice. And then melt the ice. And you're left with terraces. And you conceivably, you could have a flight of steps down as the ice melted down. And those are called kame terraces, K-A-M-E again.
Or a second explanation of how terraces may have come to be.
What happens out in front of a glacier is glacial outwash. Water and sediment is being laid down, and glaciers are sediment generating machines because the ice that was here was not just pristine white ice. It was covered with debris, and there's debris in it, and there's debris that it's pushed along in front of it. So all those reasons mean there's lots of sediment. You've got a glacier, you've got all this sediment that's being transported by meltwater out from the glacial ice, and it fills the valley. You choke a valley, just fill it full of sediment, and then later streams cut through, and they, by cutting in, they create a terrace, and then they cut further, they create another terrace. And I think it's easier to have that happen than a kame terrace, especially if you've got matching terraces on each side of the valley, matching elevations. Yeah, I mean, they could have this may have taken 500 years or 1,000 years to form this. I doubt, well, the ice may have stagnated up here that long. We don't have good dates up here. Again, it's a problem of time. I had to do this a couple weeks ago saying, we don't know. And here, I can only think of a couple radiocarbon dates up here, and they're at Bonaparte Meadows, which is a ways from us, in the peat bog. There may be, but I cannot think of a radiocarbon date or some other kind of date, OSL, whatever, up here. It's just not been studied. And so we don't know. And even if we had radiocarbon dates, we're not going to get them. The best we can get is 80 years or so. It's I'm making it sound like, oh yeah, it happened, and then other stuff. But this geologic, in the big scheme of things, it took a long time. The last thing I wanted to emphasize here is something that many of you are, I'll bet, are clued into, and that is the effects of beavers on landscapes. And Marianne Creek, I think when I first started looking at this area to come to with you folks, I had heard about beavers in this drainage. And my God, there are beaver dams here, past and present. There are and have been a lot of beavers in this drainage. And beavers are a good thing in a system that is incising. Let me say that a little more clearly. When beavers are in a drainage, they help prevent incision. They help lead to the deposition of sediment behind these dams. Yeah, it's not just the sediment. They're helping draw that stream back up near the surface where then it can move more freely. So, boy, I've become a real beaver advocate in thinking about incised areas. And so whatever the meteorologic event is, whatever the land use is that helps encourage that, or burned area or whatever, if you've got beavers down in a drainage, they ought to help prevent the incision in the bottom. And again, taking you back to the Waterville Plateau, Foster Creek there is horribly incised, and luckily beavers have come back into that, and hopefully they'll make a difference.
Teleporting one more time, now we have arrived at the junction of Havillah Road and Neely Road, where there is a view of the Sitzmark ski hill to the north and Mount Bonaparte to the south and a little bit east.
Two things that I want to talk about. One that's just kind of basic and it ties into what we've been doing so far, and the other one is a little bit of a wilder idea. Okay? So the basic one, Sitzmark here on Nob Hill, about 1972 or 1, my mom was concerned about me wanting to lay around the house and not be active, and so she got me skiing at Sitzmark. And I remember the season pass at Sitzmark in 1971 or 2 or thereabouts was $30. It was pretty cool. Sitzmark and Nob Hill. Nob Hill has an opposite form from a drumlin. It's a bedrock feature, and it has a gentle up glacier side and a steep down glacier side. And this is from glacial erosion rather than deposition. The ice moving from north to south sculpted that bedrock, and it does so by abrading the up glacier side. So abrasion like sandpaper, scouring that surface. And that's where if we could find bare bedrock north of Sitzmark up on that ridge crest, it should be striated. It should be smoothed, like just soft skin smooth, but it also should be striated with linear scratches that tell you the direction of ice movement. On the down glacier side of this pre-existing bedrock knob, it's steep because the ice is no longer pushing down and abrading. It's really, the pressure is released as it goes over that hump, and now it's plucking out boulders. And so there's two very different processes operating: abrasion on the up glacier, which is also called the Stoss side, plucking on the lee side, the down glacier side. And so now if you buy that for a moment, That landform is a French name, and I'm going to butcher it, Roche Moutonnet. And it is sheepback or whaleback is the translation. So steep, asymmetrical, steep down glacier, gentle up glacier. That is glacial scour terrain. So that's the basic story here, glacier erosion.
Turning now toward the south, we gaze at Mount Bonaparte, and more specifically at the circular valley that is apparent below the summit from this angle. Remember at the beginning, Karl talked about two types of glaciers, ice sheets and alpine glaciers. Up to this point, he has focused on the influence of ice sheets. Now we turn to the other.
Cirques form from cirque glaciers, and they are a positive feedback mechanism. That is, as ice accumulates, you get to a point where there's enough mass of ice that it will start to move down slope. It'll slide and flow, and as it slides, it makes a depression. More ice accumulates in that depression, more abrasion, more sliding, bigger depression. So you build cirques with time through that glacial erosion. The cirque is too high to be a valley. It's up on the mountain. It's circular when looked down from above. Cirques are north facing. And that makes sense, right? North-facing slopes, just like we saw on the esker back there, the vegetation was different on the north face versus the south face. Here, we're not worried about vegetation up there, but we're worried about what affects vegetation, its moisture and its temperature. And the sun at this latitude, the incoming solar radiation is always coming in from the south, so a north face is shaded to some degree, and shaded slopes are where you build glaciers first. Rock glaciers and cirques form almost always on north faces. And in the Cascades, it's just time and time again, rock glaciers and cirques, north face, south faces much less so. North faces are cooler and they preserve snow longest. So we've got an ideal place to make them. But that means that these cirques probably formed after the ice sheet was gone. And that's where things get trickier. If you had an ice sheet here that we know covered Bonaparte because there's radix laying up there, it retreats, then maybe it gets cold for several hundred or maybe longer than that, and it's not big enough to lead to a big advance of ice, but you get cirque glaciers forming up top. Conversely, these may have formed before the last big ice sheet glaciation and survived the erosion. So then that raises the question, where'd that water go? If you had cirque glaciers up there, where does the water go? Well, it's got to come down Antoine Creek. It's going to come down the Antoine Creek Gorge. It's a deep cut, 500 feet deep in places. And that gorge had to have been cut by water coming off the highlands. So where'd that water come from? Melting ice sheet, maybe melting cirque glaciers. Third, did it come from the north from Mud Lake Valley, which it's going to really seem far-fetched when we talk about it further. How do you get gorges? You got to have water flow for a long time, because if that gorge is granite, that's hard cutting. Granite, gneiss, stuff like that. There may have been tectonic activity that could help route that water in a straight line, perhaps. I'm making it sound like all this happened in one glaciation, and it may have taken several. What we also need to think about is, were there glacial outburst floods here too? Did floods, not just normal meltwater, did floods of water scour these landscapes? So to take a uniform Atarian view where you just go, well, it's just slow and you just grind it out over time? Or was it a catastrophic change as well? So I hope I got you thinking about streamlined terrain a little bit more, and then this wild idea. I have never been in those cirques, but as I look at them on maps and imagery, I'm convinced there's cirques on the north face. But they don't fit up here because we've been talking about ice sheets, and now you've got evidence for cirques up high. And then do they help drive the development of Anton Gorge down below? So I'm comfortable with that. If you have glacial ice sitting in the Okanogan Valley, you've got streams running along the edge, or if the streams were running under the ice at one point, cutting those as well. But the gorge that I mentioned, the Antoine Creek Gorge, is 500 feet deep in places, 1,200 feet wide or 1,400 feet wide. It's a prominent feature. That gorge to me is unique up here for its length and breadth. Box Canyon and North Beaver Creek are the two other big gorges I can think of in the Highlands. So it's somewhat unique, and it tells us that a lot of water came off the Highlands in what may have been a short amount of time. So that water, again, that source would be just direct glacial meltwater. It could be from those cirques, or it could have diverted from the Mud Creek Valley. It shows generally that the Mud Creek Valley lines up with Eden Valley, if you know that, and generally down to Fancher Canyon Road and Fancher Dam, I think. And then that lines up with this gorge, roughly. And so you might go, did water come all the way from Sidley Lake, Molson Lake area, straight down and into this gorge and off? There's a lot of problems with that. It's got to cross that upper Tenasket Creek drainage, but maybe that was plugged by ice or by debris leading to a pathway that was more parallel to the ice. It's also got to climb. That water's got to go up and over current topography. Maybe that topography wasn't here. Maybe there wasn't that debris. And by this, it's a lot. It's 360 feet of climb. So there's a lot of debris. So there's problems with my theory, but you've got a big gorge. You got to explain it with water. And one thing to think about is, hey, it lines up north, but we've got some problems to overcome to get it to here. So you've got a gorge that is anomalous. It's odd out here. Could this have been accomplished by a glacial outburst flood, like I mentioned up above? And I like that idea, but we don't have glacial outburst flood evidence that has been identified yet. So in the scablands to the south, in the Missoula flood affected areas, what you look for are hanging valleys hanging up on the sides of the gorge. You look for big bars of sediment down in the gorge. You look for giant current ripples that show high flow. I've not seen any of that evidence yet, but neither I nor anyone else that I know of has looked in detail either. I mean, there's more and more talk about water down in the Okanogan Valley, in the Canadian Okanagan, coming down and shaping some of these landscapes to the south as floods. So could it happen in the uplands? I think so. So that's one thought. I just wanted you to kind of get thinking about this gorge, a wild place. Maybe someday we could figure out a way to get in there and see that in more detail. It's intriguing when you look at it on the LiDAR image and on topo maps.
We started out talking about glacial lakes, and that is where we will finish. Fancher Flats is a well-known expanse of thousands of acres of remarkably flat land amid the hilly topography of the Okanogan. with Siwash Creek running along and across the south end, and Antoine Creek to the north.
I think there was a glacial lake Antoine. The glacial lake we looked at this morning, I didn't say the name of it. It's been called Glacial Lake Oliver. And I tentatively name Glacial Lake Antoine on this big flat-floored valley. It just looks like there was a lake there. And it's a big lake. This would have been a couple miles long, 2+ miles long. The evidence for that is in the water well data. So you can go on the Department of Ecology website and you can pull up well data and you can look at the well logs. And not all well logs are created equal. It depends on who logged them. The well logs for here that I've seen show as much as 20 feet of clay in the bottom of that valley. And clay is a good indicator, even though we didn't see it this morning in the Glacial Lake Oliver sediments, it's a good indicator of quiet water deposition, and that would be, ideally would be a lake. So this, I think, at one point, water was impounded in this basin, and I think it was impounded because of the constricted outflow into what I call Siwash Creek. So at the bottom end of this, Siwash Creek was a narrow outlet that would have let water out slowly. And maybe if you had a flood into here, you had water pond, and then it's released slowly out that way. Maybe there was something else going on there to impound this lake. I don't see evidence of landslides or something like that. But just the flat floor and the subsurface suggest lake. Now there is a steep drainage cut down to the Okanogan River, and there is a great big fan that pushes out the Okanogan River. So you've got the Okanogan making a big bend, and I would argue the fan of that Antoine Creek pushed the river to the west, and the Antoine Creek carved that gorge. I'm basing this on no field work, which is scary. I'm doing it just on map, but I'm saying that the creek once flowed to the south and out Siwash, and now it goes west in a more contemporary alignment. I don't have evidence for why it made that change, other than it may have, if you had water that ponded in here quickly, did that push it over a low divide and then quick down cutting to get through that. They're underlain by sand and gravel. So sand and gravel and then lake sediments on top. I'm not sure what's on top of that. It may be wind-blown sediment. It makes sense to me that you would have the high energy stuff when you had streams coming through. Once you had a lake and you flatten it out, then you're not going to have high energy. Right. But I would suspect it's overtopped with wind-blown sediment called loess. And that's what they're farming in down there. This valley has perplexed me for years. We always drive this way up into the Highlands, and I look at that flat-floored, all that ag, and you go, how do you get a big, broad, flat-floored valley? And so if you start kind of reasoning the way I reason through it, I go, okay, what do the soil surveys say? Because this is all mapped with soil surveys. They didn't add much insight other than it's fine textured soils. Then you discover the DOE well log database, and then you can go, okay, what's subsurface? And that's where the clay comes in. The lake, it wasn't all to the west side of the road. It's to the east as well in that flat-lying terrain. And going back to the fan idea, you were just talking about fire-induced high precip fans at the mouth of Lightning Creek below Bonaparte. We could do a whole field trip up here on fans. Orville is on a fan as well, on the Tenasket Creek fan. but we've driven across them all day at the mouths of streams, and they shape this landscape as much as glaciation in a lot of ways, especially the valley if you focus on valley floors. As you leave here, think about the effects of glaciers on erosion, deposition, on drainage changes, lakes, a lot of things that hopefully link together for you. And think about, I didn't really overtly do this, but we've really covered all the realms of physical geography today that I teach about back at Central: landforms, soils, water, vegetation, and weather and climate. It all links. So thank you. It was a pleasure. And please support OHA in their efforts here in the Highlands.
Blessed unrest, blessed unrest.
This podcast is produced by Okanogan Highlands Alliance. OHA is located in Tonasket, a town in the heart of the Okanogan Valley of north central Washington. We are inspired by the beauty and diversity of the landscape that surrounds us, from the aspen and conifer forests to the highland lakes to the tumbling creeks that descend to the wide, glacier-carved Okanogan River Valley. We engage in environmental advocacy, habitat restoration, and educational activities in our efforts to protect local ecosystems for future generations. To learn more about OHA or to become a member, please visit our website, okanoganhighlands.org. Thanks to Karl Lillquist for taking us on a rollicking adventure through the hummocks, ancient lakes, and glacial times in the Highlands. Don't forget to check the show notes for a link to Dr. Lillquist's field guide where you can learn more about the landscapes and landforms of the Okanogan Highlands. Thanks also to Humanities Washington and the National Endowment for the Humanities for supporting the Highland Wonders Podcast. Our theme song, Blessed Unrest, was written and performed by Tyler Graves and Andy Kingham. You can support the artist by finding and downloading the full song from your favorite music platform.
Blessed unrest.